Okay, today we will talk about the presentation. If you prepared your slides, you can do the presentation now. If you have a question and you didn't get your slides ready, I can answer your question so that you can do the presentation in the next lecture. If you want to do the presentation right now or you have any question, please use chat. Or you can, directly ask your question.
Hi, Professor. This is Anthony. I think me and my partner are ready today. I'm just waiting for Ryan Roy to log into the session. We should be able to present.
Please complete your presentation's title and author in this link. This link is actually the schedule page in our Canvas. So I just list one author who will present, one student who will present today. If you also plan to present today, you can also add a new item in the list. Any other students, if you have any question, you can ask me now.
Hey, this is Kai. I have a question of the presentation of the project.
Yes.
Yeah. For the topics that we choose, is there any like a list or limitation to the topic? I see that we, in your class, that we can choose from like the data shifting and XNOR, pop counting. Is that all we can choose?
No, we don't have any limitation. You can talk to me about your project plan.
And so what's the goal of the project plan? Like we need to design into in the Vivado of the code or something?
You can implement some functions by the VHDL.
Okay. And is this a project like last this whole semester or just for this?
Yes, it's this project will last the entire semester.
Okay.
So we will have the presentation to talk about the topic and title. So the presentation we will do in this lecture and in the next lecture should not be perfect. so that we can talk about the, the problem, the question on the topic. After that, maybe after 2 weeks, we will have some updates presentation. In those presentations, you can summarize what you have already done and what's the, limitation you realize that you cannot, fulfill the original goal, so that we can do some adjustment. At the last, we will have the third presentation to summarize your whole project.
Okay,
I had some, oh, sorry, you can go.
that's okay. You go ahead.
Okay, I had some clarifying questions. Did you make the schedule or do we tell you when we want to go?
I will, for example, I will allocate this week for you,
Okay.
so that you can pick up a 10 to 15 minutes slot in our lecture to do the presentation. You can choose to do the presentation today, or you can do it on Wednesday.
Oh, yeah, we'd like to do it today if we could.
Okay. So if someone have difficulties, we can even schedule the presentation to the next Monday.
Okay, awesome. Thank you.
We will keep this policy for the updating presentations and the final presentations. Because we don't have examinations, so this is the, the whole thing. Any group want to do the presentation, you can start now. You can try to share your screen. If you need some permission, I can also help you with that.
Yes, Professor. I think Ryan, Roy, and I are ready to go. I'll try sharing my screen.
Okay. Okay, you can do that.
All right. Can everyone see my screen?
Yes.
Ryan, can we hear you?
Yeah, hi.
Perfect. All right. Let me figure out how to do the presentation here. Was that F5?
Yeah, F5.
Okay.
Yeah. Hello, everyone. The topic that we have selected for our presentation is and our project is basically the Shift CNN, its implementation and evaluation. Can we have the next slide? So there are 6 parts to this presentation. We would be starting with a brief introduction of ourselves. We would be talking about the problem. Then we would be talking about why the problem is relevant. We would be moving forward to the proposed solutions, the estimated timeline, and finally, we would be talking about the evaluation plan. So there are 2 members in our group. My name is Ryan. I am doing my master's in intelligence systems. It's my first semester. The second member is Anthony, and he's also from the intelligence systems background. He's in his second semester. So we have all heard of convolutional neural networks. It is a subcategory of deep neural networks. As we can see at the bottom right of this slide, there is the deep learning neural network called Inception V1. So basically, this was one that was developed by Google. So as we can see, there are like 4 main subcategories of layers, and one of the major subcategories is called the convolutional layer, which is indicated in the blue color here. So this is a layer that helps with feature extraction and things like that. One of the most frequently used operations in this layer is called the MAC operation, or the multiply accumulate operation. Hence, the design and implementation of a customized FPGA or an ASIC circuit that could accelerate this operation would help us reduce computational cost, latency, power consumption, This would obviously come at a cost. It would not be free. We would face a slight reduction in accuracy, but it's a fair trade-off at this point because the reduction in accuracy is just 1%, whereas the reduction is in power consumption is 4x, which is basically 400%. And there's also a 200% reduction in the number of operations. So why is this problem important? First of all, in the last decade, a lot of progress and a lot of development has happened in the CNN field, which makes it one of the hottest technologies to be working with right now. And also, since 2017, a lot of research effort has been directed towards implementation of this architecture in embedded systems and data center deployments. What makes this technology truly disruptive is the fact that there is no need to retrain a neural network that is using the conventional architecture. We can simply use the proposed quantization algorithms to like a kind of convert a neural network that is using the conventional deep learning conventional architecture into one that is using the Shift CNN architecture. Also, this architecture is definitely more suitable to be extended to support privacy sensitive applications that may be using homomorphic encryption as the means to protect privacy. So these are some of the aspects that makes this problem relevant. Now, Anthony would be talking about a solution.
Okay, can everyone hear me?
Yes.
Yes.
Perfect. All right, so I'll go on to our solution. So as we've seen in class, we can quantize weights, we can quantize inputs, we can quantize both. For Shift CNN, we're going to focus on quantizing the weights. We're going to do that with a power of 2 representation. So this takes our continuous set of weight values and turns it into a discrete set of weight values. It turns out that the quantization algorithm for Shift CNN is non-uniform, but that's going to be okay because we've seen neural networks are good at handling some error, and the author's accuracy results are a testament to that. So for our quantization algorithm, we're going to define a code book that looks something like this set CN here. It's going to contain 0, 2 to the 0, and 2 to negative powers. I'll define some numbers up front, and then we'll do an example on the next slide. So B is going to be the bit width of the codebook index. So we'll use 4 bits for a running example. M is the number of possible index combinations. So typically we think that's 2 to the power of B. However, this is a signed value. So we have to throw away that extra negative value that we can't represent on the positive side. So that's why we have the -1. N is going to be our levels of quantization, which controls kind of how accurate we can represent our input weights. So we end up with an N times B bit value representation as our new weight. And there's going to be P possible input times weight combinations that are going to be computed by Shift CNN. So in our case, that would be 15 plus 2 or 17 possible input times weight values. So we'll do an example. So first we have to normalize the weights. We'll divide the weight by the maximum weight value. That'll give us a continuous set, but we want to turn that into a discrete set so we can calculate all the values at the same time. So we're going to quantize WI, which is equal to 0.8 to its power of 2 representation. So we'll do 2 examples. One is with 1 level of quantization, which is N equals 1. So we get one code book that looks like this, C1. It's got 0, plus or minus 2 to the 0, down to plus or minus 2 to the -6. And these are the decimal values here. So what we're going to end up doing is selecting the value from this code book that's closest to our input weight. So in this case, it's +1, which turns out we're actually off from our input weight by 0.2. That's going to be index 1 because we have index 0, +1, -1, +2, -2, +3, -3, and so on. So we represent that in binary as 0001. Now we'll represent it with 2 levels of quantization. So now we have 2 code books. You can see the difference is Codebook 1 is the same as before. However, Codebook 2 now starts at 2 to the negative 1 and leaves out that 2 to the 0 term and goes one term further to plus or minus 2 to the negative 7. So now what we're going to do is we're going to select the two values whose sum is closest to WI. So that's going to be 1 from the first codebook and negative 2.5 or 0.25 from the second codebook to give us 0.75. So now we see with additional levels of quantization, we're closer to our original weight value. We're only off by 0.05. And this is what that index would look like in its binary representation. So how do we do this? We use algorithm 1 from their paper. We see after a series of log operations and additions and some if-then statements, they define their identity function, which results in that binary representation of the weight in its power of 2 format. And in the bottom of the slide here, we see a visual depiction of the weight vector in 2D space. So with one level of quantization and 1 bit, we see our possible values are 1 and negative 1. If we increase the bits to 2, we have 1, negative 1, and 0. In subimage C here, we start to really see that non-uniform quantization. You see the large gap between the outer ring and the inner ring there. But in subimage D, we see as we add quantization levels, we actually fill in that gap and we can get closer to our original weight value. So it's important that we remember that this quantization is done on the weights. So we take a pre-trained model. We just use the quantization algorithm to rewrite the weights. And that's going to be the input for Shift CNN, which is going to be an inference application. So the inputs for Shift CNN are in dynamic fixed point format. So I had to go figure out what that was. Here's the equation for this. It's negative 1 to the sign bit times 2 to the negative FL, where FL is going to be the number of bits that represent the fractional portion, times the sum from I equals 0 to the number of bits minus 2 of 2 to the I times mantissa bit I. So why is this important? This is important because it allows us to have a dynamic range of layer outputs. So typically layer outputs are really large sums. So they're large numbers, whereas layer weights in our case are between negative 1 and 1. So this allows us to have a dynamic range of values. So on this fixed point format, we can just conduct multiplication and division with simple bit shift operations. So I'll do some examples here. So we can represent 8.5 with a fractional length of 2, as seen by this binary value here. But if we have a negative fractional length, what we're doing is we're actually assuming that we're padding some zeros on to the end of the value. So in this case, with this FL equal to negative 1, we see we're padding on an additional 0. So we can represent a larger value with only 8 bits. So we see in our example here, as we're trying to represent 8, you see the binary value that you typically would think is 2, but we're implying that we're padding on these 2 zeros onto the end. Okay, so that defines the input for Shift CNN, so for Shift CNN. So on the left, we see here a high-level structure of Shift CNN. We take our input tensor and then we send it to the Shift arithmetic unit. That's going to pre-compute all possible input or weight times input values, since there's a small discrete set of weight values, 17 in our example. We're just going to pre-compute all those values ahead of time to increase the parallelization of the algorithm. After we pre-compute those values, we go to an array of adders and multiplexers that'll use the weight to select the correct pre-computed term and add it to the bias for the output tensor. So on the right here, we see the input tensor is going to have C channels by H height by W width. We're going to write that X value to the pre-computed tensor, and then we're going to write that X value with a sign flip to the pre-computed tensor, and we're going to shift it to the right one. We're going to write to the pre-computed tensor, write that value with the sign flip to the pre-computed tensor and shift it to the right one again. And we'll do that until we have all 7 shift operations, for an example with that we've been doing. So because P is small and P is the possible weights times input values, we just pre-compute all possible values. And we're going to take our pre-computed tensor and we're going to store it in an array of shift registers to pass on to the rest of the circuit. Okay, so now that we've done the shift operation, all we have left is the addition. So we use, well, first thing we're going to do is for each output layer, tilde C here, we're going to write the bias to the output tensor. And then for each input channel 1 to C, we're going to use the weight tensor to select the correct pre-computed value using a multiplexer. And then we'll sum those up using an array of adders along with the bias that's already stored in the output tensor. And we'll have to do this for each level of quantization. So in our example, we'll do it twice. So there actually is n more additions in shift CNN. Okay, so we got an 8-week plan for our project. By 19 March, Ryan's gonna build the shift ALU and a test bench. And then by 26 March, I'll build an array of shift registers to store that output and a test bench to test that. 9 April, Ryan's gonna implement the array of multiplexers and adders and a test bench. And then 23 April, I'll implement the control logic and test bench to do a toy convolution example. We're going to try to synthesize our circuit and extrapolate our results compared to the authors by 30 April. And then simultaneously, we're going to try to rerun some of the authors' accuracy analysis using shift CNN state-of-the-art models on GPU. And then by 3 May, we'll do our final report and presentation. For the evaluation plan, we're going to have test benches for all the individual components. We're going to do a test bench to compute a toy convolution with a 2x2x3 input, 1x1x3 filter, stride 1, and a 2x2x3 output. We're going to use B = 4 and 2 levels of quantization. Once we have that, we're going to try to synthesize our circuit and identify the number of lookup tables and flip-flops and the power and relative power values. And hopefully compare those to the authors that they have in their paper. It was unclear how large an example they made for their paper, so we'll at least hope to see some similar ratios. And then finally, we're going to confirm their accuracy by using their quantization algorithm to quantize the weights for state-of-the-art models and measure their accuracy for inference on GPU. And these are our references. Any questions?
Good. Very, very concrete presentation. Basically, you address all the points I listed in the requirements. This is a very, very good presentation. Thank you. Okay. Any questions for them?
Thank you.
If no questions, any other group? So about the question on the topic selection, can you provide more details on building a sensor?
Yeah, so my idea was so you have lab on a chip devices using bioengineering to detect various biomarkers for diseases or other environmental factors. So the idea was to build some type of VHDL code that takes in and input signals and sorts them based on their input values. And you have a variety of biomarkers that you can do. And so I kind of wanted to find out if I could build a general VHDL code for picking out the more important biomarkers and making some type of output conclusion whether you can detect these biomarkers.
You don't have to be nervous because this class is the point of this class is actually provide some computer engineering background for the students who has no background in computer or electrical engineering. Are you a PhD?
No, I'm not. I'm doing the accelerated master's program, so I'm very new to this computer engineering.
Yes, I think you can. Yes, I believe this topic is reasonable for you.
All right, thank you.
You can provide more details in your presentation.
Yeah, of course.
So now I'm sharing my screen. I want to introduce a link which is a so-called it's called Colab. I will send you the link. The point of this Colab web page is to help you to train a neural network to do the inference if you have no GPU or machines. Here is just all you need is a Google account, and then you can choose to connect to a GPU in the cloud, and then you can write your Python script. For example, you can import your TensorFlow, and then you can download some of your image, and then you can load the image you download. You can do the training step by step by simply write some Python script and do some, click the button, and then you can print out. So here I defined a model, and then I print out the model structure here, the architecture of the model. And then we can add more layers and then print out the structure again, and then compile the model, and then do the training. Because I'm downloading the CFAR 10, so it's not the miniest. It's not a very large model, but it's a large model. So you need to, wait for a while, and then you can print out. You can do the inference. So I will do a tutorial on how to use this Colab. Here it starts to do the training now. It prints out the loss function, the accuracy and the loss for each approach. So you can see that the evaluation accuracy actually is increasing. So it's working now. I will do a tutorial on this to help you to use this Colab. Again, Pure's presentation do some, use the VHDL to accelerate the shift CNN. I think we can implement the CNN in this Colab. I don't think the implementation is difficult because we have the source code of CNN, just shift CNN. We need to do some very trivial modification so that we can run the shift CNN actually on this Colab. In this way, you don't need a server with GPU anymore. Any group want to do the presentation? Or have any other questions?
I think our group can go today. That's okay.
Can you repeat again?
Sorry, I think our group can go today. My keyboard was in the way.
Okay, okay. So other guys will do the presentation in next lecture, right?
Yes, I would be doing that.
Okay, okay. So please complete the schedule in our Canvas if you plan to do the presentation in next lecture. I will send a announcement about that, provide you the link. Any question?
Yeah, currently it says I do not have access to edit the page for the schedule. I was wondering if
Oh, I'm
this is
sorry,
where I
I'm
do that.
sorry. Yes, I think you can try again.
Thank you, it works now.
Okay, thank you very much. If you want to, stay here, ask me question, you can stay. Otherwise, we can complete this lecture today. Thank you very much.
I said our group would probably want to go today.
Oh, I'm sorry. I'm sorry.
Yeah, sorry.
You can share your screen.
Okay, thank you.
You can start.
Can you hear me? And see the
Yes.
screen? Can you see the screen as well?
Yes.
Trey, can you hear me?
Yeah.
Okay, great. All right, this is our project for the convolutional filter accelerator. So on to our introduction. I'm Austin Parks. I did electrical engineering at IPY, and I decided I wanted to do more of the computer engineering side of things. So I'm currently doing my MS in intelligent systems engineering here at IU. And that's because it provided an outlet to do some embedded firmware security research. I'm also interested in embedded device emulation, which kind of supports the firmware security portion of things.
I'm Trey Peterson, and I got my bachelor's at IPY for electrical engineering, and I also get my master's at IU. Main interests are FPGAs and ASIC design, and that's why I came to IU.
So on to our project background. So basically our problem lies in trying to make convolutional filtering more efficient. So convolutional filters in applications like CNNs, like you see here, can be computationally exhausting, especially when applied over a large data set of high resolution images. So you can kind of see an example of applying a convolutional filter here. So you can imagine, so this is a pretty simple example. We just have a 6x6 image. And imagine if there's like padding or something and you're applying this filter to every single square of this image. Well, that's going to be 36 computations essentially doing this, applying this convolutional filter. Well, imagine this being like an RGB image too, where it's even 3 times as large. Well, upscale this to say, a large data set of thousands of images, and each image is around 4K. You can kind of see how that quickly becomes very exhausting to whatever's trying to process that and do that computation. So this kind of brings up the importance of an accelerator, something that makes this more efficient and quicker. So it kind of saves us time in doing computations. So we can see convolutional filters have applications in image processing, convolutional networks, and more. In image processing, where you're kind of like modifying kind of features of an image or trying to illuminate features. Maybe you have an application that does this many times and you want to make it more efficient. Or in a CNN where you can expect to do convolution many times over hundreds to thousands of images. It'll get very slow if your convolutional filter computations are very slow. So we can improve this efficiency by making an accelerator in an FPGA. So we could do this with a CPU, but the CPU is pretty generic. It handles, just generic logic and execution, but it's not really tailor-made to do this sort of computation. However, we can make an FPGA very specialized for this computation so that it's much more efficient. And in the end, our goal would be to have the CPU handle like generic tasks, the other portions of a program that isn't convolution. And then we had passed the convolution onto the accelerator. And we'll see this as our project goes on. First, we're going to implement this be a CPU only, and then we're going to make a mixture of the two so that we can kind of compare, you know, our hardware accelerator to CPU only. So this leads into our project plans.
So for our project plans, we basically have 4 different milestones or goals for each subsystem. So for the processing subsystem, we would want to have our controller benchmark filtering using the CPU. So that's basically what we want to beat. And then we would want to set up the front end, or basically a way to ship these images or maybe subsets of images into the programmable logic. And that would be through, you know, using AXI4 and then into a DMA. So we would have to investigate, you know, how to interact with an AXI bus and then how to kind of build that up to interact with. Another thing is to essentially, okay, so we have this video, we display it back, and we would have to compare these 2 subsets of videos. So for example, from the CPU, it will have a higher precision than the FPGA, which we will have to tailor that precision for it. So we will be using a fixed point kind of computation on the FPGA. And then also we would want to build the Python environment on the processing subsystem, which is called Pink. And it's kind of like we would have to use Pay-to-Linux to kind of build it up for our FPGA. Now for the programmable logic, we would have to basically have that also another front end to kind of interact with the AXI bus, and that is using the AXI DMA, and then also having some sort of controller to kind of receive that image and then also pass that image onto multiple convolution modules that we will make. So one is making a convolution module, and then another one is making that convolution module scalable into multiple modules. So you can almost think of it as like a pseudo GPU in a way where you have multiple of these things doing multiple computations. And another thing is we would have to have a controller that kind of stores for memory for the subset of images or a whole image.
That leads to our processing subsystem. And this really just illuminates the Python side of things. So Pink you see right there, you know, PyYNQ. This basically provides API that kind of bridges Python to Zinc chips, where a Zinc chip is basically a system on a chip that has like an FPGA, a CPU, memory, basically everything on one chip that lets them all communicate together. And so this starts off pretty simple. Our first 2 steps are just to read a video file and extract frames with Python. And then from extracting the frames, we can branch in 2 directions. The first direction we're going to go is our CPU implementation, where again, it's still pretty simple. We're just going to apply our convolutional filter to all of these frames. The second way we're going to branch is our FPGA implementation. From extracting frames into exporting BREEAM, we're going to have DMA there as a bridge, but I kind of simplified this. And the reason we want to export these frames to BREEAM is because that's where the hardware implementation starts. Hardware can basically read BREEAM, and that's how we're going to be able to make the accelerator in hardware. So yeah, this is just the Python side of things.
So onto the programmable logic, this is a kind of rough block diagram of how data will be transferred and how the different controllers will basically distribute our images. So you can see that the AXI DMA is going to be the bridge, and that will basically pass data into the memory controller. Memory controller is basically like, okay, we have the subset of the image, we're going to pass into the convolution partitioner. Partitioner will basically take that subset of that image and basically say we could do X amount of convolutions with, you know, how many parallel we could do. And with the convoluter, that we will look into a couple different ways of doing a convolution, because there's 2 different ways we can do it. One is using an adder tree, and another way is using a cascading adder, which I predict that the cascading adder will be more computationally efficient and uses a lot less logic. Another thing is that the DSP, we will be using the DSP48 slices in the FPGA. So the DSP48 slices are like kind of hard logic blocks in there that basically have multipliers and adders, and we have to cater our precision towards making sure that those things our input data adheres to those constraints. So this is our distribution of work. So you can see that we kind of start off on opposite ends of the spectrum there. And this graph is kind of relative, depending on like, you know, if we add more goals, if we start completing stuff, or, you know, if I'm starting to struggle on, you know, the partitioner, we can have Austin kind of basically complete something that's completely separate. And then, which is like the pink setup, the CPU benchmark. And then as we start getting to the processing subsystem, kind of like framework, we would need more collaboration between us two. But say if I'm starting to struggle with convolutional partition or the memory controller, Austin can complete that in due time. So that is our distribution of work.
And that concludes our presentation. Thank you for listening. Are there any questions?
Do you have a FPGA board?
Yes. Yeah, we
Yes.
both do.
That's good. That's good. If you don't have, I can provide one.
Oh, awesome. Thank you.
Thank you.
A good presentation. Thank you very much. Any other group want to do the presentation or any questions?
Yes, I had a question. Just as far as trying to figure out how to schedule homework and stuff in the future. I was wondering how much more homework we should expect from this course, or is everything now just our project implementation?
We may have another homework. So in that homework, you may require to build some latch, some flip-flop, so that you can use these latch and flip-flop in your project. That's all. And then this project, that's all.
Okay, thank you.
Any other questions? If no, we can stop today. Thank you very much.
Thank you.
Thank you.
Thank you.
Thank you.